Okay, is done?
You are now muted.
Okay, you are not presenting, right? Now you are presenting.
I will introduce you and then you can talk. Okay?
Okay, I will start with before you get.
Okay. Well, hello, welcome to this discussion at FLUIDOS 2021 Web Congress. This dissertation is presented by Professor Carlos Corvalán and Professor Jiakai Lu. And I will talk about a very short bio of the professors. Dr. Carlos Corvalán is Associate Professor at Purdue University with appointments in the Department of Biological Engineering, Food Science, and the School of Mechanical Engineering. He received his PhD in Chemical Engineering from Universidad Nacional. He was Assistant Professor at the University of Entre, Ríos, and he held a postdoc position at Purdue University. His research focuses on computational fluid dynamics in collaboration with the industry and with USA federal agencies. Dr. Jiakai Lu is Assistant Professor at University of Massachusetts Amherst. He received his Bachelor of Science in Mechanical Engineering from Shanghai Jiaotong University and received his PhD in Mechanical Engineering from Purdue University. His research focuses on fundamental complex fluid dynamics for applications related to agriculture and food processing. His research is supported by US Department of Agriculture and Good Food Institution. We are very glad to have you both at the Congress, and thank you.
Thank you very much, Mariana, for that kind introduction. I'd like to begin by thanking the organizers for the opportunity to talk about some of the research our group has been doing for the last, say, couple of years. Our topic is quite simple. We are going to talk about the fluid mechanics of small pores nucleated in a liquid sheet. And in particular, we are going to talk about pores nucleated in sheets of complex fluids. This work has been done in collaboration with a number of colleagues, including Professor Jiakai Lu from the University of Massachusetts. And we chose this topic in part because it's also done in collaboration with Sebastián Ubal and Diego Campana from the University of Entre Ríos, which is organizing this meeting. This work was supported by generous funding from the US Department of Agriculture and the Department of Defense, in large part because although we are interested in the fundamental fluid mechanics, the results can in principle be applied to several natural and industrial processes involving small pores, including, for example, the behavior of pores in vesicles or in biological membranes. As you can see, the picture on the left illustrates a pore in a vesicle. And in this case, for example, it's important to know in which case this pore will open or will collapse, because that will ultimately determine the fate of the cells. These kind of pores in vesicles are also used typically for encapsulation of materials inside the cells. Another topic or application that these agencies are interested on is microfabrication. The picture on the center of the slide. For example, nanopores are widely used for nanosensors, for analysis of biomolecules such as DNA and proteins. And it's very difficult to make a nanopore directly. So typically, what you will use is a laser that will make a hole in a substrate, as you can see at the top of the central figure. But this hole is in the order of microns, so 3 orders of magnitude larger than what we need. But then this hole is led to collapse to the nanoscale. So in this kind of application, for example, it is important to understand the rate of collapse so you know when to stop the contraction process. Well, the formation of holes also controls the dynamics of sheet breakup in spray and atomization. Is illustrated in the figure on the right. For example, for spray of agrochemicals or for the atomization of propellants in rocket combustion chambers. So what I'm going to do is to give you a quick overview of this talk so we don't get lost in the details, in the technical details later. Well, as you can see from the figure, the setting is pretty simple. A pore is just a free surface flow driven by curvature. There is a radial curvature, which is given by the size, the diameter of the radius of the pore, which tends to close, to collapse the pore. But there is also an axial curvature, which is vertical in this figure, and is typically characterized by the thickness of the film. And this curvature tends to has a different sign, and so tends to open the pore. So there is a competition between these two curvatures, one trying to collapse and the other trying to open the pore. So the set is very simple, but we found out that it shows some interesting display of fluid dynamics. We will discuss here in this talk 4 of these ideas. The first one is that if the pore is, say, sufficiently small compared with the thickness, the pore will collapse, it will contract, as you can see, for example, in the figure at the bottom of this slide. If the pore collapses, the radius of the pore naturally goes to 0, and therefore the curvature and all the stresses that are associated with the curvature tends to infinity, so they grow unbounded. So at the center of the collapsing pore, there is a singularity where the governing equations break down. And current numerical models have typically big problems handling this singularity. And so we were doing some simulations because in practical application it's important to know the velocity of collapse, as we discussed before. And as the pore collapses, the fluid should accelerate toward the center because the curvature increases. But we found that this is true, but only up to a point. We found that the length scale decreases, but decreases more rapidly than the velocity scale. So that the local Reynolds number, say the Reynolds number at the tip of the pore, in the rim of the pore, decreases. And so the pore always collapses in the viscous regime. And collapses in the viscous regime, meaning that collapses also at constant velocity, not accelerating as we were expecting. We also found that this seems to be a universal characteristic of the pores and holds even for very low viscosity fluids. So this is one of the topics that we are going to discuss. The second topic is what we call flickering pores. Even for simple Newtonian fluid, it's not straightforward to answer questions such as what is the pore size, the critical size at which the pore will start to contract. So we found, if you look at the figure at the bottom, we found that when the pore contracts, the rim, the circumference of the pore becomes sharper. And if you look at the last figure at the bottom, you will see that the pore takes a almost conical shape. That means that the axial curvature is increasing. And sometimes this axial curvature grows faster than the contraction, so the pore will start contracting, but then at a given critical radius will start to open again. in a flickering movement. So the critical radius is not only determined by the geometry of the pore, but is also a function of the fluid properties, and we will discuss that later. And the other two topics that we are going to discuss are related with complex fluids. So if the pore is nucleated in a complex fluid, complex in the sense of the material in the fluid, such as maybe polymeric material or surfactants, what we see is that, for example, when the pore contraction reduces the radius, that will create shear stresses on the rim of the pore. So the radius is decreasing rapidly, the shear stresses are increasing also rapidly. And so we found that the increase of the shear stresses when the pore collapses has obviously important consequences if the fluid is non-Newtonian, in the sense that the stresses will affect the viscosity of the fluid. So there is an interesting interplay between the contraction, the generation of stresses, and the reduction of the viscosity if the fluid is non-Newtonian. And finally, as you can see from the figure, when the pore contracts, also obviously the circumference of the pore decreases. And that means, from the practical point of view, that the area in the circumference and the area near the circumference, near the tip of the pore, will decrease very rapidly. So as the pore contracts, the area contracts very quickly. And we will show that results showing that this may have important consequences if the pore is contaminated, particularly if it's contaminated with surface active species like surfactants, because the contraction of the area will dramatically increase the concentration of the surfactants and the concentration of any contaminant in the pore. And that will change the dynamics in a very important way. So with that overview, I'm just going to turn this over to Professor Jiakai Lu. As you said, Mariana, Jiakai leads a group of studying complex flows at the University of Massachusetts, and he will be able to fill in the details much better than I can. So with this, I will hand this over to you, Jiakai. Thank you. Thank you very much.
Thanks, Carlos. And thanks, Mariana and the organizing university to give us this opportunity to talk. So following the nice overview that Carlos mentioned, I will start with a little bit of technical details of essentially what he just mentioned. So as Carlos mentioned, most of the works that we are going to, actually all of the works that we are going to show today is based on direct numerical simulations. So I will start with just 2 slides to bore you with the equations and models that we use. So for this simple systems, a pore, dynamics of a pore, we model the system using the traditional full Navier systems of equations, because we are going to model the complex rheological properties of the fluids. So the Cauchy stress tensor here involves an apparent viscosity, which we model that using a Karu-Yasuda model, which essentially is a power law of fluids characterized by upper and lower viscosity. Here I want to call the attention of you guys that the system is essentially characterized by the Ohnesorg number defined in the lower corner, and the length scale is the thickness of the sheet, and we use the capillary velocity scale to show the results. So everything that you will see is going to be in dimensionless terms. On the free surface, we model the fluid system using the kinematic boundary condition, stating that no material cross the surface, and the interface is dictated by the pressure jump or the stress jump on the interface is dictated by this Young's Laplacian equation relating the curvature, and if we have surfactants present in the systems, the dynamic surface tension is going to possibly induce the marangonic stress, which is the second term on the second equation here. And when we do this model here, our assumption is we will be looking at very dilute surfactant. So the equation of state would be linear, linking the concentration of surfactant or the contamination to the surface tension. And finally, the convection diffusion equation will be also used to model the transport of contaminated species or surfactant on the interface, which is the last equation here in this slide, including the effect of local change of surface area, convection and diffusion effects. And for when we start model the effect of surfactant, the system would also be characterized by another dimensionless number. We call this Marangoni number, indicating essentially the strength of surfactant or initial concentration of surfactant. So if Marangoni number is 0, that means we're talking about a clean interface. So I will start by showing you guys some results slowly for pore dynamics with a clean interface, which you can see Marangoni is 0, and Newtonian fluids, where n, the power law index, is going to be 1. So to start with, we'll be looking at a relatively more familiar cases in terms of the fate of the pore on the sheet, where the pore is relatively large in comparison to the thickness of the fluid sheet. Here, R0 is 50, meaning that the pore radius at the beginning is about 50 times larger than the thickness of the sheet. So as Carlos mentioned, that in this case, the radial curvature, which is essentially the radius of the pore, is very small compared to the actual curvature dictated by the thickness of the sheet. So the pore will start open and expand. And we can see that from the numerical simulation that the pressure field for this situation shows that at the tip of the pore, here the red color is high pressure. So we have high capillary pressure, and everywhere else inside the sheet of the away from the pore, the pressure is low. So the fluid is driven from high pressure to low pressure region. That leads to the opening of a pore. Here we show a little bit more of the evolution for the interfacial shapes of the same pore that's opening. And as a verification, because this is a very well studied problem, we also were able to verify and compare our shapes for another simulation conducted by Savard and Bush using lubrication models. So the figure on the right-hand side shows that at the same dimensionless time, our simulation, which is the solid line, matches very well with the simulation done in other works, to somehow give us more confidence of the results of those simulations. To further verify our results, because as the pore opens over time, we can see here in this figure on the left-hand side, the radius of the pore essentially follows a linear relationship with time, indicating that the velocity at which the pore opens will be a constant velocity. And this is indeed our familiar Taylor-Coelic velocity, as indicated on the right-hand side figure with the dashed line. And you can see here that the telecoilic velocity is essentially depending on the property of the fluid. Sigma here is the surface tension, rho is the density of the fluid, and the thickness of the fluid sheet, which has nothing to do with the initial radius of the pore. So everything that's typically larger than half of the sheet thickness, the pore would be open, and it would eventually open and reach the same velocity given the property of the fluid and the thickness of the sheet is the same. So from here, I will turn the focus to the closing pore. Now that we know that our simulation and the code is robust enough to capture the dynamics, the shape, and the details of the flow field. So looking at a pore that's relatively small, as I mentioned, in general, we would think that if a radius of the pore is smaller than about half size of the thickness of the sheet, the pore would close. This is because now the radial curvature is dominating, and you can see from the pressure field of this closing pore that close to the tip, now pressure becomes low, and the pressure elsewhere in the sheet becomes high, which drives the flow towards the center or towards the singularity, leading to the collapse of the pore. Now, this is just to show you the dynamics of the closing pore. As you can see, as the pore goes towards the singularity, as it collapses, this is an essentially accelerating event. And here, the Onozog number is about 0.04. Just to give you an idea, this is more or less for an intermediate viscosity fluids. For a millimeter thickness of sheet, the viscosity that we are looking at here is about 10 times larger than water. Similar to the opening pore, we think that because the initial pore radius at the closing and the final radius close to the singularity is of a huge difference in terms of the length scale. So there might also be a scaling or similarity shape that we can explore that dictates the closing dynamics. So we show here for several different simulations starting at different pore radius. So R0 is 0.01, 0.04, 0.1, and 0.2, all shows that the pore radius would close at exactly the same speed, irrelevant to the initial length scale. Here, the trick is we are using a new time to show the dynamics instead of the real time, T prime. T prime is what we call time to singularity. So if the pore is at the collapse time, T prime will be 0. So as T prime goes to 0, the pore radius should go to 0. Here, what we can see is that the pore radius follows a power law scale with the T prime, with the power law index being 0.57, and the velocity also verifies that it's essentially the derivative of radius over time. We look at this for also a wide range of Onozog number, essentially going to the inviscid region. So Onozog number is going to be smaller. So here we show that when we change the Onozog number, going to the inviscid limit to 2 orders of magnitude difference, we still see the same scaling towards the collapse. Now, what's interesting here is that the scaling towards the collapse, the power is 0.57, which is a little bit different to the typical capillary and inertia force balance when we are looking at a free surface flow close to the pinch-off. That typical scale would be T radius to the T to the power of 2/3, which is about 0.66. What it means here is that because we are looking at a smaller power compared to our regular inertia to capillary force balance. This indicates that the inertia in this situation grows asymptotically faster than capillarity. We somehow also verified this situation because when we are actually looking at a pore closure, this is somehow very similar, in particular towards closing to the singularity, to another problem, that is the pinch off of a gas bubble formed. The similar scaling has also been found by other researchers, and they show that when a bubble is generated in inviscid fluids close to the pinch off, the minimum radius follows a polar scaling of T prime to about 0.56, which is very similar to what we see here. Now, what would this accelerating event do to the geometry or interfacial profile of this collapsing pore? Because we know typically the free surface flow is dictated by the interfacial shapes, right? So what we see here is as the pore is closing in an accelerating fashion, the actual curvature, or showing here is the geometry Z and R for an closing pore. The actual curvature, showing on the right-hand side, is increasing as the pore radius decreases. Here in this figure, you will need to see from the right to the left. So the pore starts at 0.2 in radius and collapses to almost singularity. As you can see that the actual curvature, which stops or prevents the pore from closing, is increasing exponentially. What this would do is, in some cases, when we have the pore that's large but not large that it will open, it's large and it goes to the collapse event, this increasing actual curvature is going to reverse the process and turn the pore around and make it open again. And we did several simulations for a pore that starts with different initial radius, and we find out that at an initial radius about 0.35 to 0.36, the pore would flip and turn from closing for a smaller radius to a flickering case where the pore starts to close, then it will open again. Noticing here that this is a dynamic process that essentially reduces the critical radius at which the pore can close or open compared to our traditional understanding of about half thickness of the sheet, which is 0.5. Right here in this case, if you start a pore of 0.5 thickness of the sheet, it will actually open instead of closing. So now that we know about how an inviscid pore would close, what about in the viscous limit, right? Here we show that for the dynamics of a closing viscous pore with Ohno number 5, which is very viscous fluid, the pore radius would close following a linear relationship to singularity. And this is much better than the inviscid case, because this is somewhat expected as we balance the capillary force and viscous force close to the singularity. We would expect a linear relationship between the radius, minimum radius, and time to singularity. But what's more important or interesting here, if we look closer to the problem, is that when we get close to singularity, from our simulations, we find out at the tip of the pore, the capillary force is essentially dictated by the radial curvature. So 1 over Rm. Rm here means the minimum radius of the pore. And the simulation also shows that the viscous stress is balancing that capillary stress at the tip is approximately equal to 2 times the velocity of the pore divided by the radius. That is tau RR, one of the terms in the stress tensor. And by balancing these two forces, we got exactly a constant value. So we got a conclusion here that when we are looking at collapse of a viscous pore, the radius is closing at a constant velocity. Not only that, this constant velocity is irrelevant to the thickness of the sheet, and it's only related to capillary viscous velocity. And we have a prefactor being 0.5 as well. So from here, we did several parametric studies to verify that if this scaling is universal enough, right? That shouldn't be affected by the initial geometry of the system. So we look at the collapsing of pores on viscous sheet that starts with different initial shapes. Here on the upper line, you have the toroidal shape to start with, or if you want to start with a cylindrical pore. Both would show that as it goes towards the collapse, or the dynamic transition part is different, they would all go to that 0.5 velocity, indicating that this scaling is true for different initial shapes. Also, we conducted simulations for pores that starts with different initial radius, 0, and they all go to the same constant velocity. Again, verifying this universal scaling of the pore collapse dynamics for a viscous sheet. So a very short or small summary here is when we are looking at a closing pore on the sheet, right? If it closes, on the inviscid limit, we know the dynamics follows a scaling for the minimum radius to the power of T prime of 0.57, indicating that inertia dominates in this situation. And if we are looking at a pure viscous case, we will be having a constant velocity, and the velocity is equal to half of the capillary viscous velocity. Now, what about the intermediate viscosities, right? One of the interesting things for those free surface flows that involves the pinch-off, or when it gets close to singularity, because the length scale of the flow changes significantly. We oftentimes will see something called the dynamic transition for, we call dynamic transition. Showing here is of the simulations that we have for a closing pore at intermediate viscosities. The Onozog number is about 0.04, and by following the minimum radius over T prime time to singularity, we do see two scalings exist in the same situation. At the beginning, because the pore is mildly inviscid, so it starts to show the inviscid scaling. And the points here in this figure is actually an experiment that we got from a pinch-off of a bubble at the same Onozog number. So it somehow also verifies that these two close of a pore and pinch of a bubble are very similar phenomena. And from the experiment, you also see that quickly the process adapts the inviscid scale, and it departs from the inviscid scale very quickly, right? From our simulation, we see that it gets close to the singularity. The viscous force, if you remember, which is also scaled with 1 over r, dominates the phenomenon, which is why that we see a viscous scale at the end of this process. This can also be verified by looking at how the velocity at the minimum radius versus radius for the same case. Here on the left-hand side of this figure is to show that the velocity essentially accelerates as the pore collapses, looking from the right of the figure to the left of this this x-axis. And at the end, velocity becomes constant and is exactly 0.5, which is our familiar closing velocity for viscous pore. We verify this also from another angle by looking at what we call a local Reynolds number. We know that Reynolds number typically defines the importance between the inertial force and viscous force, right? So if the dynamics transits from an inertia dominated situation to a viscous dominated situation, the Reynolds number would change. So if we define our local Reynolds number based on the velocity at the tip of the pore and the radius of the pore, which are the two characteristic length and velocity for the system, we show that the local Reynolds number starts at a high value, indicating that this is the time that we have inviscid scale. And at about the same time, it crosses 1 right here and goes to a very small value, indicating that we are actually entering the very viscous region locally and recovering the viscous capillary velocity for the close of a pore. And if we use our inviscid scale into this local Reynolds number, what we would see here is that for a very inviscid case, this local Reynolds number would always go to 0 because the radius would decrease in a way that's much faster than the increase of velocity. So by running simulations over several Onno's numbers that's of relatively low viscosity, we see that as we reduce the Onno's number, the velocity would increase then decrease during the collapse of the pore. However, they would always goes back to the constant velocity, indicating that the dynamics transits from the inertia dominated case to the viscous dominated case. Another thing that we look at here is that if we show the velocity field for a collapsing pore, let's focus on the right hand side of this slide. The same case that we see before, as the pore closes, the pattern or the flow field of a closing pore would change also significantly, going from a relatively pressure-driven flow, which you have a nice gradient of velocity going from low to high, to a flow field when we goes close to the viscous dominated region. And we find out that this flow field is very much similar to the flow field in the viscous dominated case. The difference here is that one starts to show this flow pattern early, and the intermediate Onno's number case shows this flow pattern late. Although we don't have a clear explanation of why we would have this strange flow field for the viscous case, we do also see here that in particular for the viscous case, when we get close to the pinch off, there's a huge velocity gradient close to the tip, indicating that the shear stress over there is going to be huge. That leads us to the pinch off closing dynamics of pores are shear thinning fluids. Here, if we run a pore on a fluid sheet of thinning, weakly shearing and BM7, I should mention that here on the right hand side of the slide, we model the fluids in using a Karuya-Suda model. So the apparent viscosity mu would decrease as the shear increases in a power law fashion. And here in this case that we're showing, N is 0.7, so that's an intermediate shear thinning or weakly shear thinning fluid. During the process, as the pore closes, and if you remember the shear increases close to the pore tip, the high shear is going to reduce local viscosity significantly. As you can see here, blue represents for about 10% of the zero shear viscosity. So what that would do to the dynamics of the pore closing is that low viscosity is going to make the pore close faster, similar to a inviscid case. That's actually what we see when we compare the two cases, two pore closing cases, one on Newtonian fluids and the other on non-Newtonian fluids. As the pore closes, the pore that's circulated on the Newtonian fluids, characterized by shear thinning behavior, would have a accelerating pore speed compared to the pore that's on the Newtonian fluids, which eventually goes to a constant velocity, right? If we show, if we run simulations over a wide range of power law index, what we actually find is that at different power law index, as the pore closes, if you look at the figure on the left-hand side, different power law index would give different scalings for how velocity is closing is related to the pore radius. And if we look closely by showing the instantaneous power to this curve on the right-hand side, we can see at the end, when we get close to the singularity, all of the cases would have a nice power, constant power. And the power law index, not the power law index, the power of this scaling follows a relationship with the power law index n value, which is exactly n minus 1 over n. That this will be a good strategy for us to obtain the shear thinning or non-Newtonian property of certain fluids when things becomes difficult to measure in a regular rheometer. Now that we also know what's happening for a shear thinning fluid, let's look at the pore that's closing on a surfactant contaminated sheet. Before that, let's look at how the convection diffusion equation is modeling this transport of surfactant on the interface. As I mentioned here, three effects. Change of local areas of surface, which is the second term in this equation, convection, the third term, and diffusion. And typically diffusion is important. So in our simulations, we would make a huge picnic number to eliminate the effect of diffusion, which leaves us to a competition between local change of surface area and convection. And we suspect that as the pore goes close to singularity, because the radial curvature or the reduction of the radius is huge, the local change of surface interface is going to dominate, which would lead to a very low interfacial tension close to the tip. What we find in our simulation also verifies our hypothesis. And if we run a model with a very small Marangoni number, remember when I talked at the beginning, Marangoni number can be thought of as surfactant with very low strength or very dilute surfactant concentration at the beginning. We still see a nice effect. For the case with surfactant, the pore velocity is going to reduce as it goes to the collapse compared to a case with clean interface. And we feel like if this is true, and we also show here actually the local tension, how that changed during the process. And we see that the surface tension on the interface reduces significantly and sharply close to the pore tip. And on the right-hand side of this figure, that is just the distribution of local surface tension on the interface. Here, because we are also looking at a large surface tension gradient, what that would incur is what we call the Marangoni stress. However, we think that the change of local surface area is still dominating. There shouldn't be too much of influence of the Marangoni stress to the dynamic process. To verify that, remember that we have our constant velocity of the closing pore. If the only thing that's relevant here is the local drop of surface tension, the velocity is going to follow approximately local surface tension divided by 2. That's also verified from a large number of simulations for different Marangoni numbers showing here in this figure. Here on the x-axis, what you're actually seeing is how local surface tension changes as the pore closes. So it will start with a large value on the right-hand side, indicating at the moment when the pore is still large, which goes to the left-hand side when the pore is relatively small. And this figure actually suggests that the only thing that's relevant for the closure of a pore on a surfactant contaminated sheet is the drop of local surface tension, and the Marangoni stress here in this situation is not relevant. So that brings me to a small summary of what I just showed. So here we see that for an inviscid pores, they would close at an accelerating speed, following a scaling indicating that inertia would asymptotically dominate over the capillarity. And if the pore closes on a viscous sheet, it would close at a constant speed. And for pores that's on the intermediate viscosity sheet, there is a transition between the inviscid region towards the viscous region. And for pores that's collapsing on shear thinning fluid sheet, they all show an accelerating closed fashion similar to the inviscid situation. And we find that there is a very nice relationship between the power law index N and the power between the radius of the pore during the closure, hinting that there could be some nice strategies that we can explore to measure the rheological property of certain fluids. And finally, also see that when surfactant is present in the sheet, even with very, very little amount of surfactant, the pore velocity is going to be retarded due to the local accumulation of surfactant close to the pore, driven by the fast contraction of the radius. And with that, I would like to thank you all for attending. And again, I will close by also thanking the support from the funding agencies and all of the collaborators from Purdue University and the hosting institution. And we will be happy to answer questions if there's any.
Okay, thanks, Jiakai. I think Herman Dresser, you have a question? Yes, Herman Dresser asked, are the profiles also set similar as in the pinch of case?
Yes. Profiles, it's not very interesting to show, but we do see that the profile is self-similar. However, as far as I remember, Carlos can fix me if I'm wrong. For self-similarity shapes, there are two scales. Here, essentially what we find is it's self-similar in radial direction. And in the axial direction, there is no significant scales, so that we were not able to collapse all the profiles together along z directions.
We'll wait for Herman is writing now. Herman says, I remember some being asymmetric in the axial direction in the Tinkoff case. Do you also have asymmetric profiles?
The axial directions. I think, can you clarify your asymmetric profile? Because in our simulation, we only simulate we only simulate a quarter of the pore, so the geometry is symmetric no matter what. However, if your asymmetric refers to the weird shape close to the tip, we do see that in extreme cases when say for instance Marangoni number is huge, the pore is not going to close at the tip, and it will close away from the center of the pore. I don't know if that answers your question.
Okay, Herman says, then you will never see them. Well, Carlos is now.
Okay, it's just a comment and maybe a question. I guess you are simulating only half part of the sheet, only the upper part or the lower part because of the symmetry reasons.
Yes.
Yes. So the problem looks like a sheet supported on a substrate that is collapsing or opening. I mean, here you are thinking of a sheet suspended in air or suspended in a bigger ring that connects with some boundaries because it's an infinite sheet with no gravity effects, of course. So this problem reminds me an old problem that I dealt with in my PhD some years ago with Dr. Raton, which was the collapse of a hole that produces in a film on top of a substrate, a rigid substrate. But in that case, it was only gravitational forces and viscous forces were taken into account. And I remember we obtained also a self-similar solution with an exponent similar to what the exponent that you are getting here. In that case, it was 0.76. And that was verified experimentally too. As far as I know, there were many other authors that continued with that problem along the time and also included surface tension effects. And I don't remember if as complete the problem as you are doing here with Marangoni effects. But I mean, this problem can also be applied to similar to the case of a sheet supported on a substrate with a contact angle of 90 degrees or something like that. So it could be an extension of the problem. So that's my comment. I think it's a
Thanks for the comment.
Yeah, similar problems that have been dealt, but this is very complete because you are including non-Newtonian effects and surface tension and Marangoni effects, so it's very complete and it's an advance in the subject. So I'm glad that you guys are doing this because it's an extension of those old problems. My suggestion is that maybe you could think of working this problem also with a film supported on a substrate. That could be another extension too, and I'm sure there is something else new to learn about the problem.
Yes, thanks a lot for the comment. Actually, we also realized that a similar problem to this is on a substrate, and we were conducting some simulations in that sense. And for instance, if we assume a perfect slip condition, a film that's on super hydrophobic surface, I do also see several work recovers a similar scaling that we see here, the collapse of pore. And even for the the constant velocity is also recovered if the film is supported on a substrate in our simulations. The fact of contact angle may be important, or gravity, which is something that we would take a look at in the future.
Okay. And the last question, have you tried the simulations for after the collapse? What is the flow after the collapse? Is there something interesting there in that once the pore has closed, has collapsed? I mean, there is some increase of thickness or something in the center or something like that? Something was told here before.
Yes, we did those simulations actually in a separate simulation, obviously, because of the geometry, and we're using finite element, right? So after collapse, that will become another problem called leveling, and we several simulations as well, also at the time, just to verify the code, and we were able to get nicely self-similarity shapes against theoretical results for the leveling problems. We were trying to see if the surfactant is relevant in those situations, which unfortunately didn't find anything strange, and we're looking at a surfactant-laden leveling case.
Okay, well, thank you.
Thank you.
Okay.
So can I clarify yes, can you hear me? Can you hear me now?
Yes, I can hear you.
Okay, thanks. So no, my point was in the pinch-off case, right? I remember there was some work showing that eventually you have the two cones on the two sides, and eventually it's like one of them wins, and it becomes asymmetric. And I guess you wouldn't be able to see that if you only do 1/4 of the geometry. So that may be a case. I don't know if it is here, but the geometry very close to the pinch-off is very similar, right? I guess to that problem. And I remember that. I don't remember exactly the details, but I do remember that the two cones they break symmetry, and then you end up with one of the cones pulling the other, stretching the other one. So I don't know if but that may also be the case here if you do the full geometry.
Really?
That was my question.
Sebastian Ual says you need a 3D simulation.
You are now unmuted.
Now that we're talking, it just occurred to me we
You are now
do
muted.
see in some situations that symmetricity is broken, because when we simulate the full interface, and if we start with uneven distribution of surfactant, in those cases, uneven meaning that I have maybe surfactant on top of the surface and no surfactant on the bottom surface. In those cases, the manganese stress will become relevant and the sheet is going to bend, and that breaks the symmetry. We were only able to follow a little bit for that case. Maybe that's something interesting to see in the future.
Yeah, I think following on that, I think that old paper by Lister, I believe, and Stone, and or something like that. But they show that actually becomes non-local, so that the far field, as you're saying, the far field ends up telling you in which direction you're going to go. So it could be there too without the Marangoni. Yeah.
That's
But
interesting.
by the way, but the profile remains symmetric in terms of the axis symmetry is not broken. So those numerical results were still in axis symmetric, but the top bottom was broken.
Yes.
Okay. Well, I think we have to close this session now because it is time, I think. Maybe the Professor Lu can respond the other question by email. And you contact her. Thank you very much, Professor Lu and Professor Corvalán.
Thank you.
Thank you very much.